they only associate watts with electrical energy. And I want to emphasize, no, it's any energy. It could be what we call mechanical energy, which is our gravitational and kinetic energy. It could be our chemical energy. It could be our solar energy. Or, as most common, it could also be our electrical energy. So when you see something on a light bulb that says 100 watts, that means that light bulb is using 100 joules of electrical energy every second. And maybe use isn't a good name. It never loses energy, it just changes it into a different form. So a 100 watt light bulb would be then taking 100 joules of energy every second out of the wall and then converting it into, and most light bulbs make light and heat. And so that would be converted into light and heat energy. But the total energy would still be the same. It's just no longer electrical energy. Now it's heat and light energy. And then even the light energy goes around the room and gets absorbed and turns to heat. So all that eventually turns to heat energy. But that's the last significant thing of this chapter. And I better close that up and say I probably said a little too much about that chapter, but hopefully that was helpful. And that'll give me a few minutes here then to continue and say, okay, let's get started with the next chapter. Because the next chapter, as I mentioned, is a long chapter. It is our last chapter on mechanics. And I don't want to scare you, it is our hardest one. But there's some good news here. The way the author does this one, and I think it's best, is a comparison between rotational motion and translational motion. And what I mean by that will hopefully become real clear as we get started. Because as you probably have noticed in these first 7 chapters that have to do with mechanics, we have not talked about things that spin, things that rotate, because those are a little bit harder. And so it's crucial that you really understand what we're going to now call translational motion. And so these first 7 chapters were all about translational motion. And so what we're going to do is we're going to see that to understand rotational motion, everything that we just did in the last 7 chapters on translational motion has a parallel with rotation. That's why this is a long chapter. Because everything we just did for the last 7 chapters, we're going to repeat. We're going to condense it all into one chapter. Because if this analogy works well, you will see, hey, rotations aren't that hard. And that's what I'm hoping to get across to you. That rotations really are the same thing, or at least a comparison with translational motion. So, if you understand the first 7 chapters well, then I hope this chapter, even though it's kind of long, won't seem that overwhelming. Because you'll go, oh yeah, well we did that. We did accelerations. We did velocity. We did Newton's second law. We did conservation of energy. We did conservation of momentum. All of those are in this chapter, but they focus on things that rotate. So I think the best way to begin this chapter really is with a big old chart over here. And in this chart, I will say, okay, what did we already do? What did we already do in relationship to translational motion? Because we're going to do the same thing as something spins. And so I'll say it again. The good and the bad about this chapter is that everything we've already did, we're going to double. But while that sounds like it's a lot, and it really is a lot, Hopefully it won't feel like a lot because you'll go, oh yeah, that's just the same thing. Oh yeah, that's the same thing. And so this is a good chance to kind of review here. Well, let me explain it this way. What did we do at the beginning of translational motion? We did something like this. We said, all right, let's take an object. I'll just make kind of a picture of a little cart. And we'll put the cart on a table. And we said, okay, the cart is going to move from here to here. And so we are going to say that it moved some distance d. And of course it may change with time, but what we did is we said there would be some kind of position of this object, some distance d. We also then said, well, what units would we use to measure it? And the tradition is to put these square brackets to represent, okay, what units fit this quantity. And I think you remember that we measured our distance in meters, sometimes centimeters, sometimes kilometers, sometimes blah, blah, blah. So there were a lot of different units we could use, but the base unit was the meters, and sometimes that was the best, but sometimes centimeters was the best. But we could switch back and forth. And so I would say the switching back and forth between these units was the whole part of Chapter 1. And then when we got started in Chapter 2, we talked about the position or the distance of the object. No, I guess Chapter 2 we didn't get to tell speed till Chapter 2. So this is really still Chapter 1. And I want to kind of do the same thing. Watch this. Let me grab something that can rotate. And so this wheel's kind of nice because it's on this little axis here. And I can now spin it. And I also put different colored blocks. There's a blue one, a red one, and a green one in here. So you can we can talk about different ones here. But as I spin this, why don't I just focus my attention on the blue one for right now? Okay, so the blue one's going around. And how would I describe the position of the blue one? And so maybe the blue one starts, right here. And like in a math class, this would be the x-axis. And when something then rotates, you would say, okay, well, rotate it up to here. Right? And so you would say its position, wouldn't use the word position, you would say its angle. Right? That's where it is. And so you would measure everything from this x-axis. You would say, okay, well, here it's at 45 degrees. Here it's at 90 degrees. Here it's at 180 degrees. Here it's at 270 degrees. And by the time it does a full circle, it does 360 degrees. I suppose we could have gone in the negative direction. We could have gone down this way and said, well, this position right here is a negative 90 degrees, which would mean negative 90 and positive 270 are the same position. And so what I want to do is start here kind of slow and say that the comparison between its position is then its angle. And I'll just put the traditional symbol here. Maybe I'll draw a picture to go with this translational motion. And then just say, okay, if it moves, then this right here is its angle. And this is a long way for me of saying, when we go to measure the, quote, position of a rotating object, it's not distance, it's angle. And so how much did it rotate? And of course, then there would be the units that go with it. And so what units do we use to measure the angle of something? Well, I just mentioned degrees. And so I trust you know that a full circle is 360 degrees. But that being said, just like back here, is that the only units we have to measure an angle? No. Are you familiar with radians? And so another really nice set of units are radians. And a full circle is 2 pi. And they each have their advantage. I guess we get the radians from the ancient Greek and we get degrees from the ancient Egyptians. Both of them have their advantages and disadvantages. Just like meters and centimeters and kilometers each have their advantages and disadvantages. So don't be surprised if we use both of those. I'll even go on. Are there others? Yeah, actually a very nice one is just measure the amount of a revolution. If it goes all the way around, we say that's 1 revolution. And so something that only goes halfway is half a revolution. And there are others, but I'll only talk about these 3. And so what I'm trying to get you to see here at the start of this chapter, because if you see this first step, I think the other ones fall into place, is that everything we've already done from chapters 1 through 7, we're going to repeat here today in chapter 8. That's, again, why chapter 8 is a long chapter. But when you see the comparison, you'll say, oh yeah, that just totally makes sense. That's why the author goes so quickly. That's why I'll go kind of quickly as we go to Newton's second law and we go to conservation of angular momentum. And we'll see the parallel between conservation of angular momentum and conservation of linear momentum. We'll throw in energy. There'll be a kinetic energy of rotation, just like we got done talking about a kinetic energy of translation. We'll have a kinetic energy of rotation. And so again, everything we've done for the last 7 chapters, we're about to repeat. And if you can see the analogy between the two, it really makes things simple. And that's what I want to make sure I get across. Now, before I keep going, because I would say this is kind of the comparison between chapter 1 here, giving its position. We learned back in chapter 1 how to convert from centimeters to meters. Maybe I should mention, just as we go along, isn't there a conversion and a connection between degrees and radians? Or between radians and revolutions? And there is. Maybe the best way to do that is to say 360 degrees is the same as 2 pi radians. And then if you divide both sides by 2 pi, on this side you get a radian. And on this side, you must get something very close to 57, because that's kind of the standard to memorize. 360 divided by 2 pi is 57.3, to be a little more accurate. And so I would say, if you know it in degrees, can you convert it to radians? In the same way, if you knew the distance in meters, could you switch it to centimeters? Of course, another option is to say 360 degrees equals 1 revolution. And so again, if you knew it in degrees, could you get it in revolutions? Or if you knew it in revolutions, could you get it in degrees? And of course, that third option would be to say 2 pi radians is equal to 1 revolution. And so I'm hoping you're seeing here, without me doing too much work here, because we probably got to move on time-wise, is to say I can convert from degrees to radians to revolutions in the same way as I can convert from meters to centimeters to kilometers. And so the angle of something is how we'll represent the position when something is rotating, as opposed to something that is translating, we would represent it with a distance. Okay, well, I'll keep going here. And then we'll take our break here But in chapter 2, we learned then about speed or velocity. We said the velocity, or at least the average velocity, is distance divided by time. And we measured it in meters per second, or even other units. We could have done kilometers per hour. And I could keep going here. But if you think about what we were doing in chapter 2 is this. We were saying, at what rate does it move? And so we took the distance and divided it by time. And we got things like, when I was doing this, if you go back to the videos where I was kind of imagining myself moving across the room, I was saying I'm moving at a rate of 2 meters every second. And so when I went here, I went 2 meters in 1 second, and then 2 more meters the next second, and 2 more meters the next second. And so in those 3 seconds, I just went 6 meters. And so that's what we meant by velocity. Well, we can do the same thing when it comes to an object rotating. Let me come back to this wheel. Let me come back to this blue little square here. If this thing is spinning, I could ask this question. Not its translational speed, but what is its rotational, or sometimes called angular speed? And so, looking at this picture, as this thing is spinning, I would ask then, at what rates is the angle changing? I would call this then its rotational speed. Or sometimes we just call it its angular speed. And I'm hoping you could see it would be the angle divided by its time. How much did it move in that 1 second, or 1 minute, or 1 hour? And so I would have something that would look like this. Angle per time. And it would be measured in what units? Well, I hope you can see the comparison. I might do something like, how many degrees per second did it rotate? Or a more common one that you've probably come across is, how many revolutions per minute? Usually abbreviated as RPMs. And so if you have a hard drive on your computer, and you look at the specs there, it may say that, hey, this hard drive spins around, and a lot of them are 7,500 RPM. Meaning it spins around at 7,500 revolutions in 1 minute. Some of the faster ones are 10,000 RPMs. But they're telling you not the translational speed, because that hard drive isn't translating, it is rotating. In fact, some of you might even have what we call a tachometer on a car. Do you know what a tachometer is versus a speedometer? I bet you know what a speedometer is. A speedometer tells you what? Your speed, your translational speed. How much distance did you travel? If you're going 40 miles per hour, that means you would go 40 miles in 1 hour. But if you look down on your gauge cluster, you might see something called a tachometer, and you'll see the engine, and it maybe will say 3,000 RPMs. Or maybe you're at a red light and it's just kind of idling, so it says 500 RPMs. That's a tachometer. See, a tachometer is not measuring your translational speed. it's measuring the speed of the crankshaft that it goes around in a circle. It's a rotation, and so that crankshaft in the engine is going around at a particular speed. It's a rotational speed. And the units that are usually used for that is RPMs. And so like I said, at an idle, it might say about 500 RPMs. And so if you could get inside your engine while it was idling and count it as it went around, in 1 minute you would say it goes around 500 times. And I hope, again, I'm not spending too much time here, but I'm hoping you see the analogy so I don't have to spend too much time here, that a rotational speed is really the same idea as a translational speed, except we're just looking at things rotating instead of translating. And when you begin to see that, you'll see this chapter is much easier than it first appears. And that's why I wanted to go a little slow here at the beginning, and we'll take our break. And we come back, we'll go a little bit faster. But before we take our break, I want to just point out then, what symbol shall we use for rotational speed? I certainly don't want to use a V, because if I use a V, that is going to confuse people. They're going to think, well, wait, speed, are you talking about translational speed, or are you talking about a rotational speed? And I'm talking about a rotational speed, so I need another symbol. And here's something you'll see going forward. That to help us understand rotational mechanics and how it is different from translational mechanics, we like to use the Greek letters. I'm sure you've seen theta in your math class and maybe other science classes many times. And they use the theta, and you probably just accepted it like, yeah, okay, so we measure our angles in the Greek letters. But there is a bigger pattern here that you may not be aware of, and you're going to see here today, is that let's use any of these new quantities that have to do with rotation, let's use the Greek alphabet. So that is not a W. That is an omega. Okay? And so the omega is the symbol that we will use for the angular speed. And so the math and the thinking for translation and rotation are the same, but the units and the symbols are different. Because there are some things that are different about rotation than translation, as we'll see after the break. But a big one I want to do right here before we break is just point out then that the symbol I'm going to use for rotation speed is the Greek letter omega. And I know it kind of looks like a W on the whiteboard. Part of it is the whiteboard and part of it is my writing's not very clean. But that is not a W. In fact, I get at least face-to-face, when students come in and ask questions, I can tell right away how much they understand when they said, I really have been struggling with that W in class. It's like, oh, yeah, you are really struggling with that W, because it's not a W. It's an omega. And everything on the rotation should be listed that way as a rotation. Well, as I said, I talked quite a bit here, and so I should call it quits, and we'll pick this up in about 20 minutes and do the second half of today.